cold, so I'm not feeling my best, but we'll plow on. So we're going to cover 3 questions. It's mainly, we're going to talk more, we'll do some derivations on the screen, but it's more so for you to ask questions and to just give some general feedback. So as we go through, you can ask any questions you've got. We're going to cover 3 questions. Section B, question 3 from 2014 to 15, which is this one up here. And then we will do, I've not got it all down. Question 1 from section A, and question 1 from 2016 to 17, and question 1 from, where is it? Yeah, and then question 1 from section A, 2017 to 18. So again, for the Piazza board, it would be useful, I mean, I'm happy to give feedback, but it would be useful if more students could interact. Like, it's not just for me to give you answers to the questions, but for you all to work together toward getting to the answers to the questions, and then I can give feedback. So at this point now, I mean, it's up to you how you revise, but I would be working on past exam questions and going over the exercise questions, and then looking at your notes and so on, and asking questions specifically when you've got a certain part wrong in your answer. So how I used to revise was, you do a question, say one of the exercise questions, do it from scratch without looking at your notes, and then look at the answer and then see which part you got wrong, and that way it stays in your mind as opposed to just looking at the solution. So I would be at this point starting to practice answering questions as opposed to just sat reading the notes over and over. So let's start with question, so has everyone got the exam with them? So if we start with question 3 from 2014 to 15, which is about vector models. So part A and B relate to the start of lecture 5 when we looked at vector models, and then part C to F are looking at you specifically to derive some of the properties of the Var 1 model. I should see. Okay, so let's do question 1. Sorry, 3A from 2014 to 15. So we've got the structural form equation B times YT equals gamma XT plus UT. And it tells you here that YT is a 2x1 vector of endogenous variables. So these are the variables that are determined within the system. So this is 2x1. We have B, which is a 2x2 non-singular matrix of constant coefficients. And again, non-singular, so it means it's going to be invertible. So we've got a 2x2. This matrix B will basically give you the interlinkages between the y's. So we're going to have y1 and y2 like this. So you didn't need to write this in the exam, I'm just to give you a bit of a broad recap. And then you can think of this B, it's going to be kind of B1, B2, B3, and B4. Oh, not this again. Times Y equals then gamma, which again, so on the right hand side we've got an X which is assumed to be 2x1, and again we have a 2x2 matrix of coefficients, and then we've got the error term. So this, if you write it out, you can think of as, say, gamma 1. And all it does, as always with these vector models, it just stacks it all into a succinct form. So again, we can read this n off line by line. So we've got a shock U1, which is a shock to equation 1, and U2 is a shock to equation 2. So we can see that on the left-hand side, we're assuming that these are the exogenous variables. So these are determined with outside the system, namely they're exogenous, so they're going to be uncorrelated with the U1 and the U2s, both of them, each of them. And on the left-hand side, we've got all the endogenous variables. And this B matrix gives you basically how they interlink. So the key variables of interest, I mean, you could normalize B1 and B4 to 1, which sometimes people do, but the crucial ones for the dynamics are B2 and B3. So B2 gives you how Y2 affects Y1, and B3 gives you how Y1 affects Y2. So then this gives you how the endogenous variables are related to each other. Anyway, but in terms of answering the question, it asks you to derive the reduced form. So what is the reduced form? Well, the reduced form is in essence solving for y. So the reduced form in general is to rewrite yt as some, and you can call the label, you can label them anything, is to write it in a form like this. So this is the reduced form. In essence, we want y. We want to solve just for y. So we can see on the written in this way, we can't. This isn't solved. This isn't the equation for y. This is the equation for b times by y. So it's relatively straightforward. We can just use this equation and multiply both sides by b to the minus 1. So we can see then. So in essence, to answer the question, we want to find what is pi and what is epsilon in this particular example. So this is what the question was getting at. So this is really should be a straightforward question. And a lot of the exam questions are structured so that the earlier parts are relatively straightforward, and then they can tend to, it's not an exact science, but they can tend to get more difficult as they follow on. And often the questions can follow on from each other as well, but not always. So you can see straight away it's just basic linear algebra. So if you multiply both sides of this equation by b to the minus 1, then we're going to have b to the minus 1 times b of yt equals b to the minus 1 times gamma xt plus b to the minus 1 times ut. So I'm having issues with the pen. So then we're going to get b to the minus 1 gamma xt. So what would be a crucial thing to note here in the exam? So what have we times ut? So this is the correct answer, but but you'd lose a mark here if you didn't note something else. What's the reason that we can do this? So again, this just becomes the identity matrix. So again, this just then becomes yt equals pi xt plus epsilon t, where pi equals b to the minus 1 gamma and epsilon t. The only thing that we're saying, we can do this because b is non-singular, so we can invert the matrix. So you'd need to state that as well. So you're given this in the answers. This was key. So this, in essence, you would get 4 marks for this, and it'd be an extra mark for noting doing the derivation, and crucially noting that we can do this because b is non-singular. So again, when you're doing this, always make clear why. Every time you go from one line to the next, you've always got to make clear why is it that we can perform this action. So this is, I think, relatively straightforward. So we can see then is that we can run, so this would be an equation where we can estimate pi. So the thing about the reduced form is we can always regress y and x and work out this pi matrix. You could just do 2 separate regressions, one for y1, regress y1 on x1 and x2, and you can regress y2 on x1 and x2. And that's going to give you these 4 coefficients in this pi matrix here. So we can estimate these pi's, pi1, pi2, pi3, pi4, but the question is, if we want to try to identify this system, if we want to estimate the b and the gamma, well, we've only got a limited number of equations which to do that. So this is going to then link on to the next question. And namely, if we want to identify b and gamma, namely the structural form, then we need to start placing restrictions on these b's and the gammas, which relates to the next question. So in his 1980 paper, Macroeconomics and Reality, Christopher Sims criticises the use of linear simultaneous equation models for macroeconomic forecasting and policy analysis. So what are his 2 main criticisms, and what do you recommend instead for these purposes? So again, you need to be familiar with the notes that Alistair wrote on this. You don't need to know it in great depth, but you need to know the overall outcomes and the conclusions of the paper. So what are the problems here then? Well, there's two. We've already talked about one, is that if we want to work with this linear system here, this, and we want to work out B and gamma, well, all we can really identify is pi. So the first problem is that we need to make restrictions on these B's and the gammas. So often we set these B's to 1, which is just a normalization really. So if we can set these to 1, which is relatively innocuous. But the point is that even setting these to 1, if we want to work out B2 and B3, the interlinkages between the y's and these 4 coefficients here, well, we've got 6 parameters to estimate, but we've only got 4 equations to solve. We can work out this pi matrix, which will give us 4. You can think of this as giving us 4 separate equations here. So we need to set at least 2 of these b's and gammas to some pre-specified value. So for example, we might assume gamma 2 equals 0 and say b2 equals 0. And if we knew that was the case, well, in that case then we might be able to solve for the b and the gamma. That's just a necessary condition. Think of it in a linear algebra type way. A necessary condition to solve is that we have to have at least as many equations as unknowns, and then the rank condition has to hold as well. So, but at a minimum, we'd have to set 2 of these coefficients. We'd have to specify them, and we don't necessarily know what they are. So that's one problem, is we need to make these restrictions on these parameters in the system, where often economic theory they'll not come from economic theory, and they could be wrong. So if you set b2 equal to 0 and b2 equal to 1, well, of course, and you will have a misspecified regression. You will then estimate b3 incorrect, and you'll estimate all the rest of the gammas incorrect as well. So another problem with it is that when we break up this system into the endogenous and the exogenous variables, we need to know which are the exogenous variables and which are the endogenous variables. So another problem is we don't always know how to separate the endogenous from the exogenous variable. So if you think about this as a macroeconomic system, and you had in there, you wanted to look at the relationship between interest rates, GDP, consumption, government spending. Well, how do we know which ones are exogenous? Which ones are determined with outside the system? In most situations, policy variables and so on are all determined together. So the government determines their spending and their borrowing and the interest rate, well, the MPC, and so on together. So it can be very difficult to say this variable is exogenous. And the problem with that is that the more endogenous variables we have, then we're going to have a problem. Because the key problem is trying to work out these B2 and these B3s. So if Y2 was exogenous, then there wouldn't be a problem, because you put that to the right and we could estimate the relevant pi matrix then. So there's two. The two problems are, one is we need to make these parameter restrictions in order to identify the parameters of the structural system, which in general we never know if we're going to be wrong or not. So it's inherently not identified. The other one is that it's difficult for the analyst or the researcher to know which variables are endogenous and which variables are exogenous. So they're the two main problems. So again, this would answer the first part, but don't forget the next part as well. So in this particular year, this was given 6 marks for the first bit. You'd get 3 for each. So one for noting that the model is not identified in general, because you need to make these restrictions on the parameters and we can't be sure when they hold or not. And then the other one for not knowing which variables are exogenous or endogenous. So this would be the other one. The next part then, well, he recommended instead is to work with Var models, which gets around this problem. So the Var model model's got other problems in itself, is that it's not really, the parameters don't normally have economic interpretation and so on. So this also has downsides, but it doesn't have the problems of not being identified, and we don't need to work out which variables are endogenous and or exogenous. So this would then get you the full 9 marks. So are there any questions on that then so far? So I think these are relatively straightforward. So if you'd read Alistair's notes on this, then you would have been really aware of the two main criticisms. And again, the first part really is just basic linear algebra. So it should, again, so these kind of exam questions you should really be getting right on most of the marks. So you don't really want to be losing marks on these relatively easy questions. So the next question then, we're starting to look at the properties of Var models. So you've got a bivariate var where epsilon t is white noise, and you're given the variance covariance matrix where epsilon t is 2 by 2 matrix of constants. Assume that yt is stationary. So in this particular example, you could, as we did in the lecture, recurse back and keep recursing back and back and back again. And because it's stationary, we know that phi to the j will tend towards naught. So you could do the back recursion, you keep going back and back and back and then solve. But because it's told you that yt is stationary, then because yt is stationary, well, we already know that e of yt equals e of yt minus 1, because they've all got to be equal. So this follows from the first assumption in the stationarity condition. Well, we also know that the epsilon t is white noise. So e of epsilon t equals naught by the white noise assumption. Taking those two things together, then we can take expectations on both sides of the equation. So we can plug in yt onto the right hand side. And expand it out. Technically this follows by the additivity condition. You could state that, but because it's such a fundamental result, you don't actually need to state that one, but there's nothing to lose by saying it. So the next line follows by additivity of the expectation operator. Again, you don't need to state this one, but there's nothing to lose by putting it. And then we can use these two conditions then. So because by this condition here, this equals e of yt, and this equals naught. So this equals alpha plus phi times e of yt. And again, you link the two. So it's because of these two here. So you make it very clear that this gives us from this line to the next. Okay. Well, and then you solve. So then you just take this to the left. So we're going to get I minus phi times e of yt equals alpha. And then the crucial thing is, because it's stationary, then the inverse exists. And then we can solve. The next thing is to invert both sides. We're going to get e of yt equals I minus phi minus 1 to the alpha, noting that the inverse exists. Because yt is stationary. Namely, it's not going to blow up. If it blew up, then it wouldn't be stationary. And we've already seen that before. So we can see straight away, and this is it. So, and again, so just to be clear here, you can only do this because the question has told you to assume that yt is stationary. If you had to verify that yt was stationary first, then the other way to do it would be to go back and recurse and recurse and recurse. So, but you can solve it this way because we've already been told that it's stationary. But you can't verify that this is the result in general without first showing that it's stationary. So that's just to be clear on that. So if the question hadn't told you it's stationary, you'd first have to verify that it was stationary, and then you could use the result. So this, in many ways, simplifies the analysis because you can just use this result straight away and then solve. Okay. And I put this down here as well, so you can see. This was taken from the solution. So again, this is what was put in the notes. But again, you'd be expected to do the derivation. This is just the summary for the marker. And again, remember that this theta to the 1 is just this I minus theta. And again, the L, because it's alpha's constant, it will just, when we multiply it, will behave as if L equals 1. So it's just exactly the same. This would be the theta 1 here to the minus 1. So any questions on that? So again, that is again relatively bread and butter. It's the pretty standard. Is that part D? Yeah, so this is pretty standard. So again, where's part D then? A, B, and C, really, these are relatively basic results. So deriving the mean, again, this would be taken as quite fundamental, and the first two parts are also quite fundamental as well. So you should really not be losing too many marks on these types of questions. Where's part D? Okay, so the next part then is to explain how you would derive the, let's do it here. Part D asks you, how would you derive the predictors? How would you calculate the two-step predictor for YT, that is? So again, well, you just plug in, it's giving you what the predictor is. And again, you should know this anyway, but it's actually given it to you in this particular question. Again, just to simplify, just given the information set, where the information set is equal to YT minus 1. So this is a definition of the predictor. Well, you plug in YT plus 2. Well, what's YT plus 2? YT plus 2 is equal to alpha plus di YT plus 1 plus epsilon t. And so then plug it in, we're going to have y hat t plus 2 is equal to, so again this is also relatively straightforward and basic, plus di yt plus 1 plus epsilon. Once you're given the formula, all you have to do really is plug in yt plus 2. You know what yt plus 2 is. So again, even if you work it through step by step and don't think of it, even if you think, okay, I've forgotten about prediction, you can just work through what you've been given in the question. Just plug it in, and even if you can't get to the final answer, you can still get quite a lot of the marks just by doing a lot of the steps. Given it, and then, well, it's just going to be alpha plus di e of yt plus 1 given it plus this next part, which we assume is not. Okay, so in this particular question, this doesn't follow by y noise, but you just make, sorry, that should be epsilon t plus 2. Okay, epsilon t plus 2. So we assume this is not, which is in essence the zero conditional mean type assumption. So again, white noise doesn't imply that. So for this particular question, it didn't actually ask you to show this. You just needed to state how you actually, for this particular question, you wouldn't have lost marks if you didn't note this, because it only really asks you is how do you derive the predictor. So you just need to really state the formulas for this question. But in other questions where the question is asking you to actually derive the predictor and state the assumptions under which it holds, then you'd be expected to say that we need to assume that this is not. So this follows from the independence assumption. However, so this assumption is stronger than this assumption is stronger than the errors being Theorem correlated, but is weaker than the independence assumption. So if you assume independence, and this follows automatically, or you can just assume that this is not directly, which is all we need, but it does not follow from white noise. The distinction between the three in practice is actually relatively mild, in that once one of them holds, they tend to all hold. So, but this is not really relevant for this course. So we have then, well, we can see straight away that this is just the predictor at y hat t plus 1. So then we need to work out what that would be. Well, you could do the whole thing again, but y hat t plus 1 is just going to be alpha plus phi of yt, and now yt is known. So that's it. So then these two together will give it. So to work to how do we, so the question is stated is explain how to calculate the two-step ahead prediction for yt. So it's not actually asked you to derive the predictor or to show why the predictor is a certain way. It's asking how would you do it. So this is really all you needed to get to here. So we needed, this would be the crucial part to the answer, is that we have y hat t plus 1 is a linear function of the predictor from last period, and the predictor from last period is just some linear combination of the previous yt, and yt is observed. So therefore we'd first calculate this, and then the second step would be to plug this into here. Okay, any questions on this? So this again is relatively straightforward. You're just using the form that's been given to you and just recursing and going back once and then going back. So this should be relatively straightforward. Even if you forgot about prediction and zero conditional mean assumptions and so on and so forth, you can still really work with the definition you're being given to get that y hat t plus 2 equals this, and then just derive y hat t plus 1, noting that yt is observed. So that was a key thing to make clear here. Okay, so part E is pretty much just bookwork. So I've just cut and pasted out from the notes. So the first thing is, well, derive the mean squared error. So there's there's a few steps missing here. So this is just an outline, but the key thing is to make clear that this, so this should go up earlier on. So call this M2. Well, the definition of it is this. So it's E. There's not really much point writing this, it's down below, but okay, then we need to work out both of the elements. So you first work out this, what yt plus 2 minus y hat t plus 2 is. Well, this is yt plus 2, and this is y hat t plus 2 from before. So again, this question follows on. So again, in a particular question, you need to use your answer from part D. And, well, basic algebra, we get this. It's just a shock from t plus 2, which is always going to be there, because we can't predict what the shock's going to be, plus phi times this, which is, in essence, the mistake, which is a forecast error from yt plus 1. So then we need to work out what the forecast error is. Well, you do the same thing again, so you work it out. So this is yt plus 1 here, and this is y at t plus 1, and it's just a shock at t plus 1. So you plug it all in then. So this here is equal to epsilon t plus 2 plus phi of times epsilon, where's it gone? Okay, plus times epsilon t plus 1. And that's all it's done here. It's just plugged this in. So it's plugged it in here, and then times a transpose of it. So again, the key thing here is to not make any the most common way once students have got this far is to start making algebraic slips. Quite a common thing was to write, instead of this, was to write phi squared e of epsilon t plus 1 dash. So of course, unless phi is a scalar, it does not behave like that. So we get when we remember matrix multiplication, you multiply the vector by the transpose of the vector. So you never, in a general vector case, in a 2 by 1 example like this, you can never ever take out the phi squared like this. So if you see this in the exam, then you know that you've made a mistake. So that was actually quite common in a mistake. Okay, so typically that's not this. Okay. So here you're using matrix vector algebra. Okay, so you're going to get 4 terms. You're going to get epsilon t plus 2 times epsilon t plus 2 dash here, and then so on. You're going to get epsilon t times epsilon t plus 1 dash psi dash, and which you're going to get this term here, and so on. So you're going to get these 4 terms, and then you start to use the white noise assumption. So because epsilon t is white noise, well, this term is not, because it shocks from different time periods. So this would be the white noise 3, that the errors are serial correlated, vector serial correlated, and that the product of the shocks, the vector product of the shocks in expectation, is just the variance covariance matrix. And this holds for any I, so therefore it holds at t plus 1. It's put I here, but I mean, really you could put 1 because that's the only one that we need. And then that's it. So this would be this. Sorry, it's put I. Sorry, because it's put I because there's 2, right? So you could put for I. It holds for any I. So you could just state that, but really, yeah, actually, technically, you should write here for I equals 1 and 2. So it holds for any I, but for our particular example, we need it for I equal 1 and I equal 2, because these other 2 become 0, so they drop out. So I would advise you wouldn't. It's fine to do this cross and slash out as long as you make clear that they're not, and then you go down to the next line. But you've always got to expand out first. So you wouldn't want to start crossing out earlier on, and then always make sure you put a sufficient amount of detail and you're doing all of the steps. So don't rush to the end of the answer by crossing things out. So the best way is to go line by line, say they're not, these 2 are going to equal not, and then you get to these 2 terms here. Okay, so once you put the sigma in here and the sigma in there, the other 2 are not, so you're going to get this term. So again, I mean, there's quite a lot of derivation there. Not that the actual intuition and the derivation itself is kind of easy, but it is a relatively textbook standard type answer. So if you've done your revision and you've been practicing, then there's not really much excuse, I think, for not getting a lot of the marks on this question. Okay, so this is why it's really crucial that you start practicing. And the more that you practice relatively standard questions, then the more likely it is that you're not going to lose relatively easy marks on the exam. Okay, so any questions on this? So we've done this in an exercise, we saw it in the lecture, it's relatively straightforward. Okay, and then finally then, so for the last part, you just need to state the answer. So, and state why. So because it's stationary, then y hat t plus h will just converge to its unconditional mean as h goes to infinity. So the crucial thing, a common way to make a mistake here is to not say why the result holds. So you get the answer right, but this doesn't hold always. It's because it's a stationary model. Okay, so that's part 3. Okay, so let's move on to the question 1 from section A in 2017 to 18. So the first part A and B are about seasonality, and then part C goes on to ask you to derive the properties of YT. So describe what is meant by deterministic and stochastic seasonality in the context of a quarterly time series process, and detail the differences between the two. So again, it's just a brief answer here. Again, don't forget to answer all the questions. Another thing, even on the Piazza board, but especially in the exam, some people didn't mention the distinction between the two. So always make sure that you've read the whole question and that you're answering all the question before you move on. So, this is again, deterministic seasonality is a form of seasonality where the seasonal patterns over the quarter that repeat every year in a fixed way, so it's non-random. So, and you could give an example. So you'd give the broad definition and then give an example, but it wouldn't be sufficient just to give an example. So the example you could give, well, it'd just be this here. This would be an example of a model with deterministic seasonality. So you'd say something along those lines in words. There's a repeated seasonal patterns over the quarter that repeats year on year in the same way, that doesn't change. It's fixed, it's non-stochastic, and you could then give an example. So for example, yt equals alpha 1 d1t, and of course you need to define the dummy variables, but okay, so you define the dummies, of course, and then plus epsilon t, where alpha 1, at least one of the alpha doesn't equal naught. At least one of these alphas are not equal to each other. In that particular case, this would be a seasonal model which would allow deterministic seasonality. So for example, if alpha 1 was greater than alpha 2, then the mean in quarter 1 will be bigger than the mean in quarter 2, and this will repeat every year. So this seasonal pattern happens every year in a deterministic and non-random way. So stochastic seasonality then is a form of seasonality where there's a pattern over the seasons, but this eventually dies away. So it's a form of seasonality that eventually dies away. So for example, you could have a seasonal AR1. If you had this model, this would allow correlations only. This would allow only non-zero correlations at lags 4, 8, 12, 16, and so on. Where if the 5 thaw is less than 1 in absolute value, then if there's a shock one quarter, let's say theta 4 is positive. If there's a positive shock to yt, then 4 periods ahead, on average, that would lead to higher than average output 4 periods ahead, and so on and so forth, but the effect would eventually die away. So if let's say that phi 4 was 0.9, then if there was a big shock, then 4 periods ahead, there would be on average, it would be higher than its mean on average. Then at 8 period, that would also be higher than its mean, but again it would be a blunted effect, and then at 12 and 16, but eventually that would die away, which is distinct. So therefore the difference between the two is that the deterministic seasonality repeats year on year in the exact same way, whereas the stochastic seasonality, the effect of it eventually diminishes. It eventually goes away. So that's the distinction between that's. So again, you'd give a broad definition, it could be one sentence, and then give an example for both, and then that'll be 2 marks for each, and then a mark for commenting on the difference between the two. So assume that yt is a quarterly seasonal time series is generated by the following process. So again, this then is a model which allows for deterministic seasonality, and I guess the question's assuming that this allows for the stochastic seasonality. So this would be the stochastic part, this would be the deterministic seasonality part. And again, just to make clear that another difference, which you could technically have said between stochastic and deterministic seasonality, is that deterministic seasonality is relatively innocuous to assume. Namely, if take sales data, then we know that sales in the UK around Christmas are significantly higher every year than they are in January. And this repeats year on year, and it has done pretty much forever. So in that particular case, it's pretty innocuous to assume that deterministic seasonality will take that form, and that would be a form of seasonality that we'd need to control for and deal with. When it comes to stochastic seasonality, it's not always as obvious as to which. It's not always obvious which part. Is it yt minus 4? Is it yt minus 1? Is it both of them? So we don't know which. If there could be stochastic seasonality. For example, as I gave, let's say that if there's higher than average sales one Christmas, then people may remember that, and they may end up spending more next year because they spent more last year. and that effect may eventually die away. In that case, it might be a model like this. So you may be able to motivate it that way. But in general, how do you know that it's not coming from quarter 1 or quarter 1 and 4? So really, the stochastic seasonality part is kind of much harder to identify, and it's much harder to motivate than the deterministic seasonality part. But in terms of this question, it just told you that this is what we're assuming is a seasonal variation in y, and then epsilon t is going to be everything else over and above that. So the dqt is a quarterly dummy variable that takes value 1 in quarter q for 1, 2, 3, and 4, and not otherwise. And epsilon t is white noise with variance sigma squared. So 1 and 2 should be straightforward then. So if yt and 1 exhibit deterministic seasonality, what must be true about the coefficients? Well, there is no seasonality if they're all equal. If they're all equal, then alpha 1 equals alpha 2 equals alpha 3 equals alpha 4 equals alpha, then yt just equals a constant plus the rest of it. So it's that at least one of the alphas are not equal to each other. So that would be part 1. So there is deterministic seasonality if one of the alphas is not equal to each other. Part 2, briefly outline how we would perform a test of the null hypothesis that there is no deterministic seasonality. Well, the key here will be to state the null. So the null is the alternative, at least one alpha not equal. Well, that'd be straightforward. Just regress yt on the 4 dummies and then do an f test of h0. So again, it's only 3 marks, so you can infer that it's only it's said briefly outlined, so you wouldn't need to go into any more detail and state. You could state the formulas, the sum of squared, residuals, unrestricted, minus restricted, and so on. You could state that, but that would be more detailed than was necessary. So in essence, you get 1 mark for the null, 1 mark for the alternative, and then 1 mark for stating that you do this regression and do an f, and then an f test of that restriction. Okay. So part C then, suppose that yt station. So there was a question on Piazza on this, and the student made it more complex than was necessary. So the key, and again, always, I know that it's obvious that you read the exam question, but read it and actually take it in and think about it before you move on and answer the question, because sometimes you can end up doing more than you need or make it more complex than is necessary. So suppose that yt1 is stationary. What does that mean? Well, if it's stationary, then, so if yt from here, if it's stationary, then we know that the mean has to be equal in all time periods. Have I missed a part out here? Sorry, there's part C, there's part 3 as well. So state the conditions in alpha q and phi 1 for yt to be stationary. Well, for it to be stationary, well, the mean's got to be the same in every quarter. And this has got to be less than 1 in absolute value. If those two things are true, then the mean's constant every quarter, and if this is the case, well, yt just equals alpha plus phi 1. In which case we've got an AR1 model with white noise errors, so the only thing left then to verify is that the variance is finite, which we can show by showing this holds. So remember, once you've got an AR1 model with white noise errors, then by definition, all of the stationarity conditions hold, constant mean, constant variance, constant covariance function. The only thing left to verify is that it's not explosive, and then we can show that by, you don't need to do it in this particular, you don't need to do it for part 3, but the only thing left in the stationarity definition is to show that the variance is finite, which we can show by verifying that phi 1 is less than 1 absolute value. So you get a mark for each. Well, so then you would have used part 3 in C. If yt is stationary, then well, it's just an AR1. If yt is stationary, well, yt, then the conditions in 3 hold. So then so we're not going to actually go through this because this is just bookwork really. In that case, yt, so because it's stationary, you could state this, well, yt is just alpha, then the conditions in 3 hold, where epsilon t is white noise. So when we know, you can write, in your answer, you could write down what that means, write down white noise 1, white noise 2, white noise 3, you do this because you'd use it in your answer. That's another thing that I've noticed is some of the Piazza responses is to say that so and so holds by WM1, and they've not stated what that means. So you can't use the fact that we've defined that somewhere in lectures. You need to state what it means, because you can call them A, B, and C, 1, 2, and 3, whatever. So you can't. My calling it WM1, WM2, WM3, that's just my own personal labeling in the lectures. That's not kind of a thing. So you would need to state what the assumptions are and give them your own labels in the exam. And then okay, and it's finite. So we're not going to do, well, the MA infinity representation, well, because it's stationary, we also know that phi1 is less than 1. Well, you just back recurse and keep going back and back and back, and you'll get the MA infinity of an AR1. Then you use your answer in part 1, derive the mean, where you take expectation on both sides and use the white noise assumption. And then for part 3, you would then use the you'd need to then derive the variance of an MA infinity process. So for this particular question, you need to derive. And it says provide all details of the steps in your answer. So namely, you couldn't just use the fact that you've memorized the variance formula for an MA infinity. You need to derive it. So in this case, you need to work, and that's why it's worth 15 marks. Is that you need to work out the whole thing. So you could write out an MA infinity generically and use a tabular method and work out the autocovariance function, and then plug in the coefficients from part 1. So there'll be 2 parts of this. Firstly, derive the autocovariance function of a general MA infinity, and then plug in the coefficients for this particular example here. So namely, remember the general this is the general formula for a so this is a generic MA infinity, and then for part 1, what you would show it, and you need to explain why, obtain, so you need to recurse back, but when you recurse, you will find this particular example that this equals this. So this will be the answer to part 1 for the AR1. You would then, for part 2, take expectation on both sides, use the white noise assumption, and make sure the key thing here is to state all the steps. So for part C, there's no point really doing this because we've done this a number of times now. There's a video clip on this, it's in the lecture notes, and we also covered it within the lecture. So this is just bookwork really. So go back over your notes. The key thing is that you do need to, in part 3, state all the steps in your answer. Okay, so part D. So figure 1 on page 6 in the appendix plots a correlogram. So if you've got this, let me see, is this 2017? So we want to perform a 2-sided t-test at the 5% level that the autocorrelation of pi at lag 5 is 0, and it tells you to give full details here of the test statistic and the critical value that you've used. So, well, you go to table 6. We're going to do the t-test. So you've got to state the test statistic used. So you've got to give the formula and state it. You can't just take out the number that's been given. So you go to the back. Well, the test statistic is, as always, going to be square root t times rho hat 5, where this is the sample autocorrelation at lag 5. I'd say the commonest mistake on these types of questions is to get the hats mixed up. So the hat is for sample, without the hat is a population. So the test statistic is this, so you plug it in. So well, the sample size is 258. You'd go to the back and you get the sample correlation at lag 5, which is 0.024, which is 0.385. Okay. We're doing a 5% test, so the critical value of a two-sided test is plus or minus 1.96. So we would have that therefore, because the absolute size of this, well, the critical value is 258 times, as long as you made it clear that you're doing it like this, 0.024 is less than 1.96, we would find evidence to accept the null at the 5% level. So again, another common mistake is to make a categorical, is to say accept or reject. It's always you find evidence to either accept or reject at a particular significance level. So don't lose marks by a test is you never ever accept or reject a null. You find evidence to accept or reject. So you never, when you do research, you never assume that you're correct in that it's definitely accept or definitely reject. So we find evidence to accept the null hypothesis because it lies in the acceptance region at the 5% level, and that's because 0.385 is less than 1.96. Okay, so part 2, test the joint hypothesis that the first 5 correlations of PI are all equal to 0 at the 1% significance level, detail the test. And again, so it's key here in that you don't just take the p-value at the end and just do the test. It's asking you to state the test statistic and the critical value. So the test statistic here, q hat 5, is sigma j equal 1 to 5 square root t rho hat j squared, and you need to get the relevant critical value from the table. So what's the test statistic? Well, it's actually, if you go, let me just get, where's the table? You stated the test statistic, it's already been calculated for you in the at the back. So if you look at it, 1, 2, 3, 4, 5, it is 9.2071. You then need to find the critical value of a chi-squared 1. So let's get this. I've not got the table. Have you got the tables with you? I can't find that. Have a look. So then we would, and the key thing to note for the Q test with where the null hypothesis. So remember, you'd write the null. So the Q in this particular case, the distribution of this test statistic for t large would be a chi-squared 5. So you'd state this, and then we'd go into the I've not got it on this particular thing, but you've got it in your, I sent this out in an email, the tables for the chi-squared. So we've got the distribution tables. Okay, so you go to the back, you go to the chi-squared test. So in this particular one, the V in the table should be, if you've got the table with you, in the V is the degrees of freedom. So you go down to 5, and then you go along to the 1%. So you go to 0.99, and this will be this is 15.09. So again, you give a bit more detail in the exam, but the critical value will be 15.09. Namely, if you look at the table, so you'd want the 0.99. So the tables have been given, the tables give you this area to the left will be 0.99, and this is 16.05. So then there's 1% to the right. 15.09. So then we can see then that the test statistic is less than the critical value, so it lies in the acceptance region, and therefore we find evidence to accept the null at the 1% significance level. Okay, any questions then? People aren't saying a great deal. Has this been useful so far? Is this the part, so let's do 2016 to 17, part 1, question section A. So a researcher collects quarterly data on total manufacturing production, percentage change from previous quarter from Mexico over these years, 118 observations, and we donate the variable by product T. So briefly comment on the main properties of the graph in figure 1. Well, this is 2016-17, right? So let's well, what can we see here? It looks roughly like the mean has stayed constant throughout time, maybe around 1%. So I mean, of course, you've not been given the mean, so you wouldn't be expected to say it is. But you can see it doesn't seem to change. It looks like around what it looks to be around 1%. Wait, got a question. Yeah. If the associated output had p-values of the Q stat. Yeah, so the point is you can use the p-value to do the test, but the question told you to state the test statistic and the critical value used. So again, you would lose marks here if the question didn't specify. Yeah, but of course, in practice, then yes, you can just use a p-value that's given to you in the table. But the questions asked you to state the test statistic and to state the critical value and to do the test that way. So in that particular case, you would lose marks there because you've not done what the questions asked. Okay, so if the question doesn't specify, if it just said perform a test at the 5% significant level, well, you just write the null, you'd write the alternative, and you could just take the p-value from the back and say p-value bigger than significance level, therefore find evidence not to reject, or find evidence to accept at 1% or whatever percent it is. Okay, but this is another, and this was a mistake as well, and I'm seeing it also on the Piazza board as well, is that sometimes it doesn't seem that students are reading the question, they're kind of just wanting to answer the question that they want to answer, which of course, if the question specifies, then you need to do it the way that the question asks. And it's also key to look at the wording of the question as well. If it says derive and to provide all the steps, well, that's definitely signaling that you can't just memorize a formula and to just plug it in and not derive where it comes from. So always be careful to read the question and make sure you're answering it as it's specified. So for that particular one, although you're right, you can do the p-value way, you would have to do it as a question as asked. Okay, so then comment on the properties of the graph. Well, the main thing, as always, you'll be commenting on the mean, the variance, and the covariance. And it's very broad. So look, there's not really a right or wrong in terms of, but well, when I say there's no right or wrong, there's not really, if there was a change in the mean over time, it doesn't look like it's going to be very distinct or severe. When you look at a graph, even if you do test that the mean has or hasn't changed, if you do test that the mean has changed over time, even if you do a formal test, you can always be wrong. The conclusion can always be wrong. So it's never really right or wrong, but if someone said that there was evidence that the mean has drastically changed, then that would be incorrect. But the answer would be expect you to say that there looks to be evidence that the mean has stayed constant or relatively constant through time. So there's not really any evidence here, or there's not much evidence that the mean, if it did change, it would likely not change by very much. So it looks to be relatively constant mean around 1%. It looks somewhat like the volatility has decreased after 2000 and before, so the volatility does look higher in the 80s than it does after. And again, it may or may not be right, but in terms of, even if you do a test, the test can always be wrong. But from the graph, visually, it does look like there's been a slight decrease in the variance after the 1980s. And then finally then, there is, looking at the graph, it looks to be evidence of a positive correlation on the recent variable. So you can see when the process goes above its mean, around 1-2%, that it tends to stay there for a while, and conversely when it goes under. But again, doesn't look to be particularly strong, but there's some evidence of a positive correlation with recent lags. So again, it doesn't persist for very long. So it looks like the correlation is mild, positive, and doesn't persist for very long. If it persisted for a long time, then we would expect the graph to kind of, it wouldn't be as kind of, although you shouldn't write this, but it wouldn't look as jaggedy, so it'd be much smoother. So it would stay there, and then it would eventually go down. So it'd be much kind of smoother than it would be then if there wasn't it would go on for longer. So if it stayed above, then if it was going to be above an average for 10 periods, then you'd expect it to not be going up and down as much as it does like this. So relatively constant mean. The variance looks to decrease possibly slightly after around 2000, and there is evidence of some positive correlation with the recent lags. That's relatively mild, okay, or something along those lines. So the next part then was asking you to use a correlogram of the production in figure 2 and perform a joint test at the first two population correlations are both 0 at the 5% level. So going back to your question, Edward, then in this particular case, then you can just use a p-value because it's given to you. So you wouldn't need, because it's not specified how you should do the test, then you can just use a p-value method. So you would state the null, you state the alternative, and then you would either get the p-value out, or you can do it the other way and you can get out the critical value and compare it to the test statistic. But we can see that the p-value the p-value at lag 2 is, and again, this is rounded to 3 significant figures. So it's not that it's not, but it's obviously very near to not. So again, you wouldn't say that you categorically accept or reject. But we can see, so you write the null, you write the alternative, we do the Q, you state the test, we're going to do the Q test, and we can find that the p-value is not to 3 significant figures, which is less than the significance level, in this particular case 5%, is it? Therefore we find evidence to reject the null at the 1% level. So that would be what you'd write at the 5% level, sorry. So that's what you would write here. Okay, so you'd be expected, but you'd be expected to give a little bit of detail. So you're going to state the test, state the null, the alternative, and then make clear the p-value. So, or you can do it the other way. You can state the test statistic, get the critical value, and then do it that way. Okay, but again, utilizing the Correlogram product T for part 3, the research concludes that the true process of product T is an AR1. Using only the information in figure 2, formally discuss the validity of this conclusion. Well, from this you can see straight away, wait, I'm going to use the wrong one. So, if this was an AR1, well, we know then that the next correlation should be 0.37 squared, and this should be 0.37 cubed, and so on and so forth. So remember, for an AR1, the correlation between yt and yt minus k is the coefficient phi1 to the power k, where phi1 is approximately equal to the correlation at like 1. So if this was an AR1, then the next one should be 0.37 squared, and this should be 0.37 cubed, and so on. But again, remember, these are all random variables. So it could be that this was an AR1, it's just that we've observed these, for example, both these are negative at legs 3 and 4, which they can't be if it's an AR1. But it could be that we just estimated them the wrong, it could be estimation error. So it could be that these were slightly positive. So there's no right or wrong in terms of, well, there's no way you can know whether or not you're definitely right or wrong ever. But in terms of the graph itself, there's extremely strong evidence against an AR1 here. Firstly, in this particular answer, be expected to state that if it was an AR1, then if there was an AR1, then the correlation at lag 2 should be 0.37 squared, and then 0.37 cubed, and so on. So the key thing to note is that looking at taking these estimates as being close to the true correlations, sorry. This is I've taken a copy of the exam that I had as a draft, which wasn't the final one. So this would have been page 7 in the exam. If you look at the one that I've used, this just has. So when I did, I should have used the other one. But when I did the exam, I did this with Alistair. So I wrote the first half, and then I sent it off to Alistair, and he did the rest. So then I've just used this. This is the draft that I first came across when I looked. But yeah, you're right. This would have been page 7 in the exam. But I mean, aside from page numbering, it's still the correct figure. So this is the Correlogram which the question relates to. So the key thing to note is that you'd be expected to state the form of the correlation function of the AR1. You would then make clear that this obviously is very far away from that. So we can see that we would not expect these negative. We would not expect for an AR1, all of them should be positive, and we can see another point to make here is that we can see that at legs 3 and 4 we can actually find evidence to reject the null that they're not, and where they're negative. So there's actually quite strong evidence that legs 3 and 4 are negative and strictly less than not. So we can see all things together that this is very unlikely to be an AR1. And another point is that leg 2, again, there's evidence to accept the null that this is not at the 5% level, which again also couldn't be the case. Because if the first one was positive, then the next one should also be positive and bigger than not. So again, all together, then it's highly unlikely that this is an AR1. Even allowing for the sampling error, because even accounting for the sampling error, we're still finding evidence that there's significant negative correlation like 3 and 4, which could never be the case with AR1. So they're the key points you'd be expected to make in this question. Okay, part B. So the researcher runs an AR1 regression for t equal 2 to 118 and provides a correlogram of the estimated residuals in figure 3. So using figure 3, perform a two-sided hypothesis that the correlation of epsilon t at lag 3 is 0 at the 1% level. So you go to figure 3, which is here, and you just do the standard test. So again, we've already done this. The t stat will be square root 118 times minus 0.25. Sorry, yeah. Which will get minus 2.5, which is less than the critical value minus 2.33. So we find evidence to reject the null. Okay, so again, these questions are relatively straight. So these questions on testing that a population correlation at one lag is not, well, it's just square root t times by the sample correlation. That gives you the test statistic. In this case, it would be minus 2.5. You then need to get the critical value. Well, in this case, it's minus 2.33, so you need to state that because the test statistic is less than the critical value, it's in the rejection region, and we find evidence to reject the null hypothesis. So again, we've already pretty much covered this in a similar question before. So we'd find evidence to reject the null at the 1% level. Okay, so we've done 1, we've done 2, which is to do the joint test, to do the Q test. So you can either do the p-value approach or the write out full, the test statistic and the critical value. And there was strong evidence that the production correlogram is not an AR1. Okay, so you do the test. So again, in this particular for this question here, so for part 1, we've got the null, which is row 3 is not, alternative. Again, I'm writing out, we've already covered this, lag 3, well this is the test statistic, it's square root of 118 times, and the critical value is minus 2.33 at the 1% level. So this would put 0.5% in each side. So that's how you would find it from the table at the back, and therefore minus 2.5 less than minus 2.33, then evidence to reject the null at the 1% level. So researcher B suggests that the conclusion of the test in B1 implies the estimated model of an AR1 will be an inaccurate representation of the true process. Discuss what the researcher means by this assertion. Well, we found the conclusion in part 1 was that there is evidence that there is a correlation at lag 3. Well, this just in essence is saying then that the exogeneity condition breaks down. So in essence, it's saying that the errors are serially correlated, so that it's going to be dynamically incomplete, which will mean then, of course, that the OLS estimate will be biased. So it's not. It will be an inaccurate representation in that it will be dynamically misspecified. Because we've got serially correlated errors, then the model is misspecified. It's dynamically incomplete. Another problem is that it'll be an inaccurate representation of the true process, that when we run OLS in this regression, we're going to get a biased estimate of phi1 because the exogeneity condition doesn't hold. So that's what will be expected for part 2. So this part 2 was getting at the serial correlation in the errors. So the first part 1 was in essence getting you to test for serial correlation in the errors, which you did and found evidence that there was. And then the next part is asking you in essence what is the what it means when there's serial correlation. Why is it an inaccurate representation of the true process? Then part 3 is that researcher B suggests that the correlogram of the residuals in figure 3 implies residuals satisfy this, and again where NT is serial correlated and pi is less than naught. So using your answer from B1 and any further tests from figure 3, discuss the validity of this hypothesis. So what you're going to do here then? Well, it's asking you to, what it's saying is that does the autocorrelation function imply that it's possible or likely that the true form of the error process looks like this, where pi is less than naught and NT is white noise, namely that the only correlation comes at lag 3. So this is saying that the errors are an MA3 where the first two coefficients are not, and there's just a correlation. Yeah, so for part 1, in the mark scheme, you could have done either. So you could have had 117 or 118. In terms of the test, these tests are asymptotic in that they're derived for t going to infinity. So in terms of the actual test procedure itself, whether you use t or t minus number of parameters, then they both will give the same conclusions for t large. So yeah, technically you are right, but you would get the mark for 117 or 118 in this particular case. Okay, so we've written the test statistic as root t times rho hat 3. If you did t minus p rho hat 3, well, because t divided by t minus p converges to 1, then as t gets bigger, the difference between the tests will be negligible. So you could have done it either way here. So the whole point of these tests is that we're using the central limit theorem and we're justifying that this statistic has a normal not one distribution for t large. So in essence, we don't actually know what the distribution of this test statistic is. All we know is as t goes off to infinity, that eventually it will become a normal not one distribution. So technically you can write the test either way, and they'll both be for t large, they'll both do the exact same thing. So you could write it either way here. Okay. So for part 3, it's asking you in essence to justify that the errors have this particular form using the Correlogram. So if you go to the Correlogram, so you've already answered this in part. So we can see that the Correlogram says that there's evidence at the 1% level that there is a non-zero and negative correlation at lag 3, which confirms what the researcher says. And if we did individual tests at lags 1, 2, and 3, we can find that we would find evidence to accept the null hypothesis that all of these are not at the 5% level. So the Correlogram actually does give credence. It gives validity to the researcher's hypothesis. So that's what you'd be expected to say here. It doesn't mean that it's definitely right, of course. It relies on the fact that the conclusion of the tests are all correct. But if we took the conclusions as given, then this would say that the errors would be this particular MA model here. So you'd be expected to use your answer from the earlier part that there is evidence that there's a correlation at lag 3, but there is no correlations at lags 1, 2, and 4 at the 5% level. So that's what you'd be expected to say here. So if you took all the conclusions of the test together, you would get a model like this, where pi is less than naught, because we estimated pi to be minus 0.25. So in essence, the researcher's opinion, there is validity to that hypothesis, and that would actually follow from the conclusions of the tests. So unless the tests are wrong, then this would actually be a fair assumption of the researcher. So the next part then was taking the errors in part equation 2 and plugging them into part equation 1. So we have, and it's asking you to show that it's asking you to show if the errors are, if the true model, if we run this regression here, and if the errors have this form here, then it's asking you to show that we can have this here. So this is just deriving the true form of a process when there's serial correlation in the errors. Well, the simplest way to do this was to plug it in. So we have, you can use a lag operator approach, but we have epsilon t is pi epsilon t minus 3 plus eta t. Okay, well, we know what epsilon t is from equation 1. Epsilon t is just yt minus mu minus psi 1 yt minus 1. Okay, and therefore we can get epsilon t minus 3. Just go back 3 periods. We'll get yt minus 3 minus mu minus this, and then plug them in. So we'll get, and you can do that yourself and expand it all through. You'll find alpha equals mu 1 minus pi, omega 1 equals minus psi 1. So all you're doing is plug it into here and rearrange. So this is just basic algebra. So again, even if all the wording around it, research assertion, testing, etc., but all it, if you actually read it and see what the question is getting at, all it's saying is if we run this regression here, but the errors have this form, well, what would be the true form of production? Just plug in it just then becomes a relatively basic algebra question. So again, you should be able to answer these questions relatively straightforwardly. Okay, so then part 4 was just looking, as I said, is looking at deriving the true form of a process when you've got dynamically incomplete, where there's zero correlation in the errors, and you want to work out what the true form of the model will be. So we can see that the reason why it's dynamically specified is that we've missed out these two terms here. So if we run equation 1, the reason it's dynamically incomplete is we've omitted these two variables here, and because pi is not equal to naught, we can see both of these are not going to be equal to naught. So if pi wasn't equal to naught, then W2, omega 2 and omega 3 are both non-zero, and therefore we've missed out these two variables here. Okay, but because we've assumed e to t, the error is white noise in the question, then we're done. This is just this is just an AR4 model where the coefficient on t minus 2 equals naught. So this is what this question gets at here. And then finally then, figure 4 provides the EV's output from an AR4 regression of product T. Discuss how it may use information from this output to test whether 3 hold, and perform this test at the 5% significance level. Well, if you go so how would you do this? Well, if we want to test that this holds, well, we want to test in essence that the coefficient on yt minus 2 is not. So if you go to the, here we are. So this gives you the estimate of equation . Sorry, it's here. Okay. So in order to test that it's got that form, well, we need to have that the coefficient on product t minus 2 is not. So this here is an AR4 regression in general, and we found that if equation 1 and equation 3 hold, we know then that the true output will look like this. So if both those things are true, then where is it? The true model should look like this. So in order, we can now use the table figure 4, and if this model, if the two things were true, then we know that the coefficient on product t minus 2 should be naught. So if we go then to the output we've got, we can use this and do a test. So if the two things were true, the coefficient on product t should be naught. So it's just a standard t-test. So we've got the test it, we've got the p-value. So because the p-value is 0.3158, so doing a t-test, because it's bigger, then you could do, and I don't think this question, I don't think actually, Ash, you didn't specify, did it specify a significance level? Yeah, you did. So because 0.3158 is bigger than 0.05, then we find evidence to accept the null hypothesis that the coefficient on product t minus 2 in an AR4 regression is not, and therefore there is evidence that this is actually the correct form here. So this allows you to test this then. So that's how we can, if it allows you to test in to the extent that if the coefficient wasn't naught, then we know that these two things can't be true. If equations 1 and 2 are correct, then we know that equation 3 must hold. So if we found evidence that the coefficient of product t minus 2 wasn't not, well, that would be saying that 1 and 3 can't be true together. So that's why we'd want to test the null hypothesis. Okay, so in that particular question, you'd write out. So I mean, you'd write it out like this. So you'd write product of t equals whatever. You could give them different labels, mu plus run. I'll just call it p just to be. Just call it p just to be simpler. So just call product p. So in essence what it's saying is that we run product t on a constant plus well, if the two things are true, we know that the coefficient, this should be not. If it wasn't true, then it wouldn't be not. You would then go to the back and do the test. Okay, so you can do a t-test, and the p-value is whatever it was, 0.3518 was it, but you got it at the back. This is bigger than 0.05, so there's evidence to accept at the null at the 5% level. Okay, which is given evidence that the two things are correct. Okay, so this is how you would test. This is what the question was getting at. So when you read this question, the only thing you got to do is to translate it into what is it actually asking you to do. So read the question carefully. The final part then is researcher C believes that the model in part 4 will provide a better approximation to the true process. So they specified this particular model here, then the model in 3. So using your EPRA as output from figures 5 and 6, determine whether 3 or 4 provides a better fit to the data, providing a brief justification for your answer. So the key thing to realize here is unlike the previous part, we can't do a parameter restriction test, a test between 4 and 3. Because one of them, we can see that this model here is not a special case of this model here, or the reverse. So and therefore you're going to use the key thing to note here is that we can't do a parameter restriction test, but we can use the AIC and BIC model selection criteria. So the brief justification would be that you just give a very broad outline of how you use them. So you've got the two model selection criteria. You set an upper and lower bound on the number of lags and do the test. So what we've got here. So we go here and we take the AIC and BIC out. So we've got them here, and you do the same for from this model here, which would be equation 3, and this model here, which is equation 4. So you just give a very broad outline that we can use these model selection criteria which we want to choose. We want to choose a model which minimizes a criteria which balances off the loss of degrees of freedom with the fit. So you just give a very broad outline here, but the key thing is that you get the correct outcome. So we want to choose the model which minimizes the information criteria. So we can see the AIC is 4.02 and for model 4 and 4.0385 for model 3. So it's minimized for both of them are minimized. Both the AIC and the BIC are minimized for equation 4, and therefore that we would prefer model 4 to 3 because it provides a better fit to the underlying process. Okay, so that's it. So at the end of the questions, I'll try and do another session if I can. I've got a lot on at the minute, but I'll try and, hopefully that was quite useful to give you a bit of background. Are there any other final questions on the questions that we've covered? So again, it'll be this will go onto this will upload onto the channel afterwards if anyone wants to look over it again. But I think that's everything for that. So yeah, so good luck with them. I'd carry on. As I said, I think the best revision now is to keep practicing. Do the questions without looking at your notes. and the solutions, write them out, and then look at the answers and start looking at which steps have you missed, like what parts did you get wrong, which parts may you've lost marks, and then look at your notes. So I think as time's going on, it may not be... For part B, is it? Do you mean B part 1? I don't know what, Lucas, I don't know what you mean. What's 2.58? I don't know what you mean, but just put it on the Piazza board as a question. I'm not sure what you mean. What's the which B part 2 for the for this one? I'm getting confused. B part 2 for this last question wasn't about a test. Oh, the critical. Okay. Is it? I think these were the draft solutions. Wait, well, if it's a 1% test, so you'd want to put 0. So you'd want to get 9.99. Yeah. Sorry, it should be points. So these were the draft solution, the draft exam. So yeah, the critical value is 2.58. Okay, so it's you want to, when you look at the tables, you go down and you want to leave 0.995 to the left, which would give us 2.58. So yes, you're right, it's not 2.33. Okay, so again, so you can put more. I'll try and do another session, but I think, as I keep saying, I think it's key now that you practice previous exam questions and the exercise questions, and then start looking at your notes for bits where you're struggling or for parts that you get wrong. So that'll be my advice for the best way to revise. Or if you are gonna, I mean, it might be useful to read certain sections again, but I think just going over the notes again and again will not be as effective as doing practice questions and getting used to writing answers. Yeah. So it should be. Sorry, I took the draft solutions and the draft exam, but it's 2.58. The critical value is 2.58. You still get the same. When you say will there be, I mean, I can't say there's been questions that's technically examinable. So yes, but yes. So that was a part of the course that would be examinable. So anything that we've covered is technically examinable. So apart from there was only a couple of slides in the last lecture 8 which weren't examinable, but everything else is. So there could be questions on the CQR paper, yeah, but for the Nelson paper, it's just that it wouldn't be like nitty-gritty specifics. It would only be the very, 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 very broad conclusions to the paper which were given in the notes online. Okay, so yeah, and I think was it last year? I think there's already been a question on the CQR thing, but I was a couple of years back. But yes, there can be questions on anything in the notes and in the exercise questions. Okay, so the whole course together is the notes that have been given, all of them, all of the video clips, they're also part of the course, and the slides and what we spoke about in lectures. So that's all technically examinable. Okay, but if you've got any other questions, you can put them on the PRs. So hopefully that was useful. So okay, so I'm going to go off now. But if you have any questions, then please put them on the board. It might all be useful for you to all start answering questions as well together and like to provide feedback for each other. But I'll provide general feedback from your written answers. And also, can you please try and write answers a bit more clearly, because it's difficult to read. If you don't write it in LaTeX, it's very hard to read when you just got the T's. Like, please either write, if you're going to put an answer up, either write it by hand and scan it, or take a picture of it and put it on it clearly. But don't, if you're going to do lots and lots on one, don't kind of just put 3 like badly pictured written outputs in one thing. So break it down. Try and keep your questions relatively contained for each. Just do separate threads as opposed to like blasting it all down on one in one go. Either handwrite it and take a picture and have it relatively small, like just do one part at a time and upload it clearly, or try writing it in LaTeX. And it's not difficult to do because there's an equation editor, so you should be able to write the equations out. Otherwise, it's quite hard to read. But anyway, good luck with everything. I will be available on the Piazza board. Of course, you can email me. And okay, so see you later.